Good morning, everyone.
Morning.
So I've got my notes and I've got my clock. For the next hour, I, Frank Ham, have the privilege of moderating a panel on physical AI and closing the sim-to-real gap. And I'm going to take a minute just to introduce these panelists who have represent pretty diverse range of folks where physical AI is being deployed in our world today. So starting here beside me is Mahesh Kailasam. So Mahesh is Corporate VP for R&D and System Design and Analysis here at Cadence.
Yep, thank you.
And Mahesh, the physical part of SDA is where Mahesh leaves. His teams build the tools that simulate a lot of the physics that's necessary for physical AI, contact, stress, thermal, all of these things that are necessary to interact with the world. Amit Goel is next. Amit is the head of robotics and edge computing ecosystem at NVIDIA. And that covers both hardware and the software platforms they're building at NVIDIA that enable physical AI. Monica Sia is next. Monica is head of business operations and partnerships at DYNA Robotics. Now, DYNA, maybe some of you have seen, but DYNA is building intelligent, armed robotic systems that do very dexterous manipulation. And I hope she gets a chance to talk a little bit about those challenges here.
Sure.
Yeah, Suraj is next. Suraj Gajendra, some of you know. He is VP of Products and Software Solutions in the Physical AI Business Unit of ARM. And ARM, I think, needs no introduction here with this audience. And then finally, at the end, Prasoon Raha is the VP of Autonomy Compute and Sensing Systems at Rivian. And Rivian, of course, builds beautiful EVs. I thought Anirudh was going to be here this morning. I know he knows and loves the Rivian that he has. And like many of the best car companies in the world, Rivian is on a journey to build autonomy into their systems. And Prasoon is at the head of that. Okay, so I want to turn it over to you guys to have a great discussion on this. Let me set the stage for just a couple of minutes, especially thinking about what happened yesterday with the fireside chat between Anirudh and Jensen. So the LLM revolution has been extraordinary. I think we can all agree. It's a convergence of GPU hardware, the transformer and attention software mechanisms, an ocean of text, and that combination produced what people call the ChatGPT moment, a step function in capability that is literally reshaping all of our businesses. Now, the question this panel is going to wrestle with is, does it necessarily follow that a similar moment will happen for physical AI? Autonomous cars, robots working alongside us, humanoids in factories, is this just around the corner? Now, yesterday, during the fireside chat, Jensen, I think I heard him say that physical AI has had its ChatGPT moment. And who am I to argue with Jensen? That is certainly true in some respects. In fact, today I bet some of you came here in a fully autonomous car. But we also must recognize that physical AI faces many fundamental challenges, still unresolved or maybe unscaled. There's no internet scale corpus of robot experience to train on. And the task isn't just perception and language. When a robot sees a door, it has to recognize the door, grab the door handle, rotate it, understand the mechanics, the physical interaction with that world. That's the role of simulation, at least in part. And some people feel simulation is the way that this whole thing will scale. But obviously simulation has its own gap, and that's what leads to the sim-to-real gap. And so these are the things we're going to talk about today. This panel is about why that gap exists, what's being done to close it, and what it means for the people in this room. So let me get started with a question to all of you, and we can just go down the line here. I just argued that physical AI faces a fundamentally harder problem than LLMs. From where you sit, whether it's simulation, silicon, robots, vehicles, do you agree? And what's the specific moment where simulation breaks down and reality bites in your domain? Mahesh.
All right, great question to get. So I was thinking about this, after Jensen's comments as well. To answer your question, I do feel that physical AI is harder than LLM. Okay, so I think most of you have seen the movie Matrix. You download all the jujitsu moves, and all of a sudden, things happen, right? So that's not what is going to happen in the physical world. Even if you have the intelligence, even if you have downloaded the knowledge of how things should work, you have to build the physical systems to be able to react to whatever you've learned and interact with the world. So there's a fundamental difference between LLMs and in the real world, in the physical AI, which is that the embodied, the physical object has to react to what happens in the world, has to be able to carry out the motions, mechanisms, everything, whatever it might be, in time for it to matter. Coming to simulation, I think simulations come a long way. I mean, obviously I'm biased. That's been my life for 30 years or more. But when it comes to physical AI, again, there are gaps, right? So there are certainly, everybody talks about contact. Sometimes simulators we make approximations because maybe it's for performance reasons, maybe it's for other expediency reasons. So you might model something as rigid instead of flexible. And all of these tiny things add up. And so what might work well in your simulator with all those approximations fails when you go to the real world, because the real world, the object, whatever you're building, might not be rigid. You have to take into account contact. And contact is not just two bodies coming into touch with each other, right? So you might have different kinds of soil conditions, snow, ice. You're walking, you're doing things in a different environment. Yeah. So that interaction of the body with the real world and how the real world pushes back, I think, is fundamentally important to capture in a simulation. And then you have to build that body as well, right, that product. So that's why I feel physical AI is inherently more complicated than LLM. Yes, you need the intelligence, but there's also the complexity of building something that has to operate in the real world.
It's a pretty complicated world.
Yeah, exactly. So,
Amit, how do you see that?
It's adding to what was mentioned earlier. We see there are 3 or 4 big problems that differentiate physical AI from digital, right? First is, in the digital world, we know the inputs was texts and videos, but the physical world, just the modality of data that we are talking about is very different. We're talking about forces, we're talking about contact, we're talking about friction, we're talking about audio. It's a multimodal problem, and that entire data set for that is continuous and really huge. So if you look at the number of tokens, if you tokenize all of this information from the physical world, it's orders and orders of magnitude more than the text tokens that exist in the world, right? So what that means is you need to have training infrastructure and models that can understand from all of this different modalities of data, right? That's one big difference compared to LLMs. The second big difference is, as you mentioned earlier, the lack of data, right? For LLMs, everything was encoded, everything was digitized. For the physical world, we have data, right? We have people observing things, capturing stuff all the time. So we are capturing the physical world, but how do you make it encoded in a tokenized that sort of model can learn, right? So collecting the data is hard, tokenizing it hard, and that's where simulation is absolutely critical. That's the way you can get ground truth. You can, if you can make compute the answer to the data problem, we're going to have a lot of compute. And that's the most efficient way to get data and scale data. So the simulation is important for data. Simulation is important for validation. How did we all get to experience our first LLM? We just got it on our phones, and if we didn't like, we could just give a thumbs up, thumbs down. Can't do that in physical world. It's too costly, too dangerous, too expensive to just vibe test your model. You got to put it in different environments. Simulation is absolutely critical. I can't think of anybody building a physical AI model and just shipping it out without actually simulating what it's going to do in an adversarial scenario.
We'll definitely come back to safety later in this discussion.
And then and the last piece is it's just how do you distribute it? You need edge compute. You absolutely need intelligence on the device. You cannot because the thing is dynamic, you have robots, you have cars, you need to have AI running on the device that is 24/7. So that's the third problem. So at NVIDIA, we are trying to solve that by building the platform. We built the 3 computers, one for training, one for simulation, and one for the edge inference.
Excellent. How about you, Monica? Where does the rubber hit the road with simulation and the Dexterous stuff that's going on at DYNA?
I know. I got that question every day. Yeah, the ChatGPT moment, or is it only a transformer moment? I get it every day. Okay, I work through with AI, including the last generation, pre-LLM AI. And what I feel like is happening in the world of robotics is that, on the one hand, I think while we are talking about how this wave of physical AI is benefiting from the bigger wave of AGI or LLM, but you will find that actually the people who actually are working on robotics, actually, I still think that, even including us, don't have enough connections and lessons that we can borrow from development of LLM. I think that part is still very underappreciated. For example, how do you scale to thousands or tens of thousands of GPU cluster? What are some better lessons you have seen in scaling a very large scale model, whether it's VLM or video generation, word model, however you want to call it. There are a lot of experience and lessons that we can actually borrow from the AI side. However, on the other hand, people who come from that pure AI background, who work on LLM, they might underappreciate a lot of the things in robotics, how to make things work in the real robot, hardware. The complexity of hardware is very underappreciated, right? The why whole body control, the control system is so hard. So I think on the one hand, I think the combination of these two words are still early, but I think that's why it's still very exciting, because there are still so many things that can happen, and we have already seen the signal. And talking about simulation, so I think that simulation is a very interesting problem, because given all the new technologies that we are seeing, there are many new ways. Sim to real gap has been a forever topic in robotics, right? Yeah. But in this new world, there are many new elements coming in that enables us to think about it in a different way. For example, evaluation, like what I just talked about. When you were not developing a general purpose model, you can just go into some a specific use case, right? And I can just eval on a specific use case. Why do I need to go to build simulation to make that work? However, for example, now we are building the general purpose. So even though we are working with a handful of customers, but we still want to test general capability of our model, testing across thousands of, if not tens of thousands of use cases. So simulation, even though it's not perfect now, will still boost our efficiency greatly, which was not the need in the past. And not to mention, Frank, we also briefly talk about, right, how this generative AI, agentic capability of LLM will also reshape how we think about the investment in building a simulation environment. So maybe we don't actually need to 100% solve the solve sim to real gap in order to really enjoy the huge benefit from simulation. But I think, to be honest, the industry is still relatively early in that respect.
I think that's fair. You touched on the constraints of edge compute, and that's very much on your mind.
Absolutely.
I'm sure, Suraj.
Yeah, absolutely.
Tell us a little bit how ARM comes at this.
Yeah, look, for us, I think, as they touched upon, the key from a simulation environment perspective is the scale. Simulation environment and the richness of simulation environment enables scale, right? As what Amit was talking about, just from a compute platform perspective, there is a lot of challenges, be it energy efficiency. Humanoids can't basically be plugged in to a power socket, right? So energy efficiency, the compute that's needed, safety, security, the real-time time determinism aspect of that. There is enough complexity in the compute platform itself, but then when you have to sort of enable that over hundreds and thousands of robots in a very seamless way, that is where we believe simulation environment is going to play a very, very important role. The gap will exist, as what Monica was talking about, but it's just about how do you ensure that you enable multiple different tasks? Because look, I mean, robotics has been there for a long time. Industrial robots has been there for a long time, but again, they're very fixed function use cases is what they've been enabling. Now, when you talk about humanoid robots or any other newer forms of robotics, it's more about those robotics applications are expected to do multiple different tasks, right? And those tasks are not always pre-programmed. So the idea of creating a rich enough simulation environment that you can then sort of use to understand the challenges of use cases like that and then enable the scale is basically what it is.
Yeah, interesting. Prasoon, how about you at Rivian?
So simulation is fairly crucial for us. There's two aspects of it, right? One is when you design a vehicle for autonomy, you've got the compute and multimodal sensor coming in. The first aspect is, when you're designing a car that you're selling to consumers, the sensors has to go in places and still look nice. So there is always a conflict between where you place the sensors. They need to serve the function of the right, autonomy input that you need for your algorithms, and as well as integrate well with the vehicle physically. So simulation serves a big aspect there in terms of, doing these what-if scenarios, looking at the field of view of various sensors, making sure we are integrating it correctly. But that's the starting point. Where we see the break is, okay, you can get an initial guess in a design, but you still have to put them on a vehicle, run them with ground truth sensors to see whether you're actually getting the right kind of data and qualify them. So that's the first aspect. The second aspect is, once they're in the vehicle and you're running the models, we ship a new model every month, for example, for autonomy. And before we ship a model, we have to run tens of millions of miles of simulation. So we have things that are called hardware in the loop that's got recorded data from all the hundreds of thousands of vehicles that are out there, and that run all of this. But still, that doesn't necessarily guarantee that you would need and cover all the corner cases. You still need to top that off with real driving mileage to see whether it's actually reacting correctly with the right latency to various objects that's coming in. So I think simulation gets you so far today, but there is still a gap in between, and maybe with more advanced AI models, we can scale that up by saying, I can run what I used to do with 10 million miles can be accomplished in 10,000 miles maybe someday, and then I can run more use cases in simulation.
Right. With an eye on safety, obviously, through the whole process, right?
Yes, absolutely. Safety is critical
from an
to
automotive company, it's mission critical.
Yeah. When the computer is driving the car, it's life and death. So we take that very seriously in terms of the kind of simulations that we run.
I think that's a big challenge in physical AI, right? The result of a hallucination is actually not just a mistake in language.
Exactly. Unlike running a model where you're generating memes, where it just generates something funny.
Consequences as well.
Consequences are different when you're in the real world. So that's the difference with
and
physical AI.
it's safety and it's security aspects.
Yeah, sure.
You don't want anyone to hack your robot, and you obviously have to ensure that data security, as what Amit was talking about earlier, and also how you basically, the model security, the model needs to be encrypted, the whole use case needs to be sort of foolproof. So it's safety from a functional safety perspective, but also it's overall data protection and the model protection.
Yeah. Fascinating. So let me. That was a great walk down the line. I'm going to get specific now with some of you in your area, but I invite anyone else who has an opinion to chime in and disagree or agree. So let me start with you, Mahesh.
Okay.
Obviously, the simulation that you've been part of for decades is now on a journey of GPU acceleration. Sure. It's getting faster, it's getting more capable. Is that going to help close this sim-to-real gap? Is it the right way to think about it, or is it something else?
I would say it's part of the story, right? So you can have an approximate simulation that runs really fast on GPUs. You can scale it, but if the results are not trustworthy, then you're getting to a wrong result very quickly, right? So it's part of the story. The other part is getting the physics correct, right? So I would go back to those of you that were here yesterday, the 3-layer cake, which is now becoming, I think it's famous and copyrighted by Anirudh. The middle layer, the physics layer, is absolutely critical. If you get the physics layer correct, that foundation correct, then the top layer, the AI, whether it's for designing your product or for training or eventually for confidence in deployment, all of that becomes easier. In fact, I would even say it becomes magical when you're able to get the physics correct, so that you don't have to eventually introduce corrections to your policies or your training logic, right? So the physics, the trustworthiness of the physics is quite important. So, but they both go hand in hand. So it's not enough if you have a great, accurate physics, but it takes days to run. So you have to be able to run it faster. So the acceleration and the physics both go together. The way I would look at it is, GPU scaling wins with speed. When it gives you scenarios that you can evaluate, lots of scenarios that you can evaluate. But engineering grade simulation, physics high accurate simulation gives you the trust.
Right.
Okay, so you need both. You need the trust and the speed in order to be able to start moving to closing that sim to real
It's
gap.
an interesting way to frame it.
Yeah,
Yeah.
and of course, there's going to be always gaps between what you observe in the real world and simulation accuracy, and so that's why you need a lot of data as well, and that's something that we've referred to before. So it's going to be a combination, but fundamentally having that engineering physics grade simulations running at scale, running on GPUs or however else we might get faster throughput, I think is going to be key to closing that sim to real gap.
Yeah, excellent. I mean, my question for you guys at NVIDIA is really about why now, right? Why, NVIDIA is obviously investing very heavily in the hardware side, as always, but the software ecosystem to support physical AI. What has happened that just NVIDIA sees this is happening now? Talk to that for a second.
That's a great question, and there are a few things that kind of converged together for us to make the advancements that are happening in physical AI. The first was actually LLMs and transformers and the ability, the scaling laws that we saw for models to learn from unstructured, unsupervised data. That was an important thing, because as we talked about earlier, the physical world is inherently multimodal. It's inherent, a lot of it is unstructured, right? And we did not know how to learn from that data, right? But with the transformers and LLMs, we figured out a recipe how we can learn, how we can scale, and build models that can understand the unstructured information. The second advancements happened in the space of simulation, right? We've been working on simulation for a long time. My experience with simulation goes back to my chip design days, where we used to run spice simulation for a transistor and then convert it into a gate level simulation, run the timing for a block, run the timing for the entire chip, and I'm super excited to see what GPU accelerated timing is going to do, because it improves the performance so much. You can test so much more. But we were limited in terms of how we can, what kind of simulations we could do, right, in the past. They were super expensive, they were super slow, and if you want AI to learn things, you need them to run really fast, right? So now on the simulation side as well, now we have the ability to run these physics simulations for robot learning, where you can compress years worth of simulation down to days and hours, right? The only path earlier was to go to the physical world and let it run, and you can't 2 years later, you cannot bring back a policy and deploy it, right? So with the physics running on the GPUs, scaling that out, we were able to bring years of learning into hours. That unlocked the ability to actually create these policies. The third thing that has also recently happened that's important is the fact that we can take reality and bring it back into simulation, or you can call it neural simulation. So building simulators that can learn from the real world, we are able to collect data, do a reconstruction, and create that environments with very high fidelity, or in fact have neural models of physics that have been learned from the real observations, right?
Yeah.
So again, the AI part of it, how AI is coming back into simulation to make simulation better. So it's not just, we have to solve the sim to real gap, but one of the techniques that we are doing that with is taking real data and bringing it back into simulation. Now you don't have the real sim to real gap, right? So that ability to take a lot of real world data, which is plenty available, right, and bring that back into simulation is the second thing. And third is fundamentally advancements that happen in the compute on the edge side as well, right? We're able to run tens of billion parameter models on the device. And we've seen this in the self-driving cars, how they all started, but the real unlock that happened is when they could start reasoning about it, because we know the physical world has a really long tail. There are lots and lots of corner cases, and in order to be deploying AI in that world, you need a solution that is self-learning. You have to do counterfactual reasoning, and that became possible, right, with the reasoning models and the compute that you could actually do it on device. So I think just all of the big bang happens because all of these things came together at the right time, and we have the opportunity to go solve the hardest problem humanity has faced.
Yeah.
Sorry,
go ahead.
Yeah, just to add to what Amit said, I think, for us, when you think about the model evolution, when you think about the use case and workload evolution, it's massive. Think about, again, LLM and beyond, and life before LLMs, and how every movement of the robot was actually coded by a software, behind it, an algorithm behind it. Because of this rapidly evolving models and use cases, again, if you think about, for us as ARM, I'm not talking about AGI CPU today, but I'm talking about ARM as the IP and technology enabler. Usually in the automotive space that I've been working on, it usually takes about 4 to 5 years for us when we launch an IP, a CPU IP for the automotive market, for a silicon partner to adopt it, and then a tier 1 and an OEM to implement that in a car, and eventually, for the car to show up on the road. Literally about 4 to 5 years since we enable the CPU IP. Now, that was okay for the world that we were living in 5, 6, 7 years ago. Now, as the workloads are rapidly changing, we can't wait for 5 years for any sort of feedback, right? So we will have to be absolutely modeling some of those use cases in the simulation world today for us to understand what those challenges are, be it power efficiency or real-time determinism or whatever, right? So the rapidly changing workloads are sort of making us think out of the box and enable some of these things in the simulation world rather than wait for the physical world to catch up. So that's
thank you.
Feels like something that Cadence can help you with.
Sure.
So let me.
So just one other point. So to what we just discussed about the bringing reality back into simulation. So at Cadence we say design for AI and AI for design, right? So this is another way of looking at the same thing. So simulation helping improve reality, and then reality capture, learning what's happening in the real world, bringing that back into the simulation world. I think that loop is going to be pretty critical for us to move as we move forward. So,
I want to turn our attention to something that I think we all love to discuss because we're so darn good at it, and that's dexterity, right? Humans really do excel at dexterity, and dexterity has different meanings across this panel. But Monica, you're probably the closest to our traditional understanding of dexterity with the robot systems that you deploy. Has simulation been central for you to achieve this kind of performance that you're seeing in your deployments? It's a lot of data, and there's gaps in simulation. How do you see that piece of the puzzle? Because the deployments that I see it from DYNA are pretty amazing with the kind of complex materials they're interacting with.
Yeah. Just a little bit context about DYNA compared to all the very established companies here. We're still relatively early. The company was founded less than 2 years ago, Series A, and we have raised like $150 million from NVIDIA and some other investors. And I think we talk about dexterity because one of the very first use case we deploy our robots to are folding related tasks, including folding napkins for restaurants, folding towers for gyms, hotels, laundromats. And of course, we are also currently working on other use cases like logistics center, etc. The reason that we choose like folding those deformable objects like towels and t-shirt is exactly because it is something that you cannot be easily solved either using traditional ML or in simulation, right? Because soft body is one of the most challenging issue in simulation. That's why I would say in early stage, like most companies like us, right? We probably haven't used like simulation very aggressively. However, the however is very important. Is that, as I mentioned, we are entering into a phase of building the general purpose robot. What does it mean? People talk about data a lot here, right? However, whenever someone say that, oh, like robotics doesn't have the internet scale data like LLM, I think there's a fundamental maybe non-consensus or misunderstanding about the kind of data we actually need to build robot. Because when you make that analogy, you are saying that we are all using all the real robot data, like teleops or like Wumi, whatever, those very expensive to collect data in pre-training. However, that's not the case, right? Just like in LLM, you use those internet data that are not super high quality, but with a very diverse, like huge amount in your pre-train, and you use very expensive data, like the data you buy from those data vendors, right? Actually very expensive for coding and many more in your post-train. And this volume of data in post-train is not the same magnitude as pre-train. Same for robotics, right? So we are using, like nowadays, we're using either VLM or like currently like video-based model. You can get it from very cheap, like internet or like relatively cheap, much cheaper than real robot in the pre-train, so that you only need to use a very high quality like data in for the post-train. Then you will ask, like, where does the simulation sit? In the past, people would say that simulation doesn't work very well because there's sim to real gap. But that's when robotics rely on very small model. So that's why you need very high quality data for that specific task. However, now if like all the other people, like all the other panelists here, right, they're working towards a more scalable simulation. That means that you can probably get to close to pre-trained level of data from simulation. Yes, there's simulation gap. However, you have much bigger volume. And using the LLM the new architecture, we can learn from that kind of data, which we could not do like several years ago, pre-LLM. That's one way to use simulation, right? Another way to use simulation is like what I said in eval. So I think combining those two, it actually gives us a new way to think about how to use simulation. And not to mention, right, like with a generative AI, it also, I think that it also makes generating more data from the same simulation environment, because the hardest thing is in building that simulation environment.
Right.
But how do you get the most from one simulation environment that you have already spent so much time in building? That's also something that can benefit from the new generative AI. So yeah, I think that that's what will fundamentally solve the dexterity in a way that's very different from the old way of like task-specific control focus.
Maybe staying on this topic of dexterity, pursuing maybe when you think about the dexterity problem at a car company, it doesn't seem obvious, but of course Rivian does more than build the cars. They build the factories that build the cars, and the factories have robots that build the cars, and the vision at Rivian could be quite large in this space. Tell us a little bit about generalization in your company.
Yeah, I mean, physical robotics is close to us, not just from a car standpoint, but just automating manufacturing and Our CEO has recently started a company along these lines, Mind Robotics, that's looking at automating the infrastructure within our factories. So dexterity is important there. But I'm going to take a step back on sort of why I think that this is like a ChatGPT moment for all of this. I started my career as an analog designer. So all the inputs that are coming in to the system like ours are analog, and the sensors, I think the physics layer that Mahesh talked about is truly critical, because the sensors are essentially evolved to the point where it can convert these analog signals into bits. And that's been ongoing. So today, the reason we're seeing this whole loop is because that entire tool chain, from analog to digital to then the compute that actually reasons about those bits, are coming together. So I think it's a virtuous cycle. And even within that, where we see the gap is you can deploy one kind of sensor, call it a CMOS imaging sensor or a radar, but the physics of that sensor is very crucial, because even today the models have to basically be trained on the specific sensor that is being used for your particular process. So whatever you call as physical AI, whether it's in autonomy or robotics, still depends a lot on the fidelity of the data that is coming in, and very contextual to the kind of sensing ability that is coming in. And we see that, if I could say I've trained my car on a single radar, but I can change that sensor tomorrow and make it work, that's the step jump in designing the systems that we need to get to with all the various simulation capabilities and modeling.
So if I may, I want to pick up on what Monica said. So I think we started by saying LLM versus physical AI. I think they actually also go together, right? So, so the point was, okay, how long does it take to set up a simulation? Can a new engineer get started very quickly to not just run one simulation, but run a bunch of scenarios and and do that very, very efficiently? So LLMs play a role there. I mean, so all the agentic workflows, so for being able to set up a model very quickly based on history, based on maybe the engineer's knowledge, but not the tool knowledge, right? All of those things play into a big role as well, and I think we saw some of that being discussed yesterday as well. So combination of LLM together with the physics-based simulations, and of course the speed up of it with GPUs, that I think is a key point to keep in mind. We're benefiting from everything that's been done from the LLM world.
Agents is absolutely going to change everything in how we do our work, right? If the challenge for developers for using simulation was, hey, it's too complex to set up, takes too long to run, and then all of that changed. And I have something that was happening a few weeks ago. We were participating with a partner on creating a challenge where they had to simulate cables for insertion into motherboards. And the initial 3D asset that was created was designed by some engineer. It had gaps, but it modeled it at capsules, and there were gaps in between. And the 3D asset in which it was doing this insertion, it had plates where the capsules could go through, right? We just gave it to Claude and said, hey, this is what's happening. It looked at it, and I said, okay, I see this problem. I'm going to, redesign this cable asset with cylinders, and I'm going to keep these chunks separate. Made the entire thing, called up our Omniverse to run the simulation to see if it's working right, fixed it. 15 minutes later, it said, here is your new cable asset. It runs perfectly fine. Go simulate it.
Yeah.
So I think the fusion of the productivity, the tools used that we have, is really going to change how we even use simulation tools.
Yeah.
Amazing. Let's turn our attention to something we touched on earlier, but it's so central in physical AI, and that's safety. We talked about how the downside of a problem with a physical AI system can be catastrophic. How are we going to build and deploy these systems so that they're safe how do we do it today? And what is the role of simulation or improved simulation in pulling that off? You know,
Yeah, I can
take a crack at that.
I can start that. So again, we're moving away from a world where robots have been in cages. I mean, literally cages in a factory setup. There's no human direct interaction with the robot, or you basically don't have any human hovering around, or loitering around the robot. So from that sort of a setup where safety is sort of forced in the overall system, and also if the robot malfunctions or gets into some sort of a weird state, you have steps that it needs to follow to come to a safe state. So there is very methodical, here's what you do, and this is how it works. To now, where we are expecting robots, and even in the case of autonomous driving, or even in case of other forms of robots, it's no longer in a cage. So it's literally, and there's a lot of interaction between humans and the robots. And of course, I mean, especially in the case of autonomous driving, there is a huge question of life and death, right? You absolutely have to make sure that when your car is driving down the freeway, you sort of have all safety mechanisms completely active and monitoring. So again, there are multiple different ways you actually handle it. You can actually handle the safety much more robustly in the hardware, but that's too expensive when you actually try and do that, right? You can't have multiple different SOCs and managing and monitoring each other, because it's cost to the overall platform and stuff like that. So the way we look at it, Frank, at ARM is obviously, for us, it's all about the use case. We start from the use case, and then we say, okay, for our technologies and our IPs to be able to enable, say, in an NVIDIA chip or any other partner's chip, we will have to understand what is that end-to-end use case from a safety perspective, where in that end-to-end use case we can actually ensure that there can be reliable and more robust safety mechanisms implemented, be it in the algorithm, be it in the software, be it in the hardware itself. And how do we sort of contribute to that safety case by ensuring that at least the core compute elements that we deliver are robust enough and safe enough, right? And of course, it's not just the compute elements that we deliver, we also deliver aspects of software test libraries and other things that can then sort of keep those CPU IPs and other forms of IPs that we deliver constantly monitored and checked within the use case, what the use case allows you to do, right? Because you can't, again, you can't allow a CPU to go into a reset mode or a fault management mode in the middle of a use case as well. So you really have to sort of program this very well, understanding what the overall use case is. That's the way we actually monitor.
Right. I'm sure you have some thoughts on this, Prasoon.
Yeah, very much along the lines of what Sanjay was saying, that the applicability of safety, you have to design your hardware system in order to have the right level of inputs and redundancy, but again, have the hooks within it to be able to monitor what the system is doing.
Yeah.
Is it, it's like introspecting yourself continuously and keeping yourself in check with a very low latency cycle. So I know that 2 steps from now, I would be making a mistake. So you design a system such that you're able to predict what's going to happen. And that's true for the variety of LLM models and the hardware systems that work together conjointly. We would have a set of inputs that are going in that do the perception of the world, prediction of the path, and then the trajectories, right? So all of these are happening concurrently, and can I predict that I'm going to make a mistake and that's going to cause a fault? So that's the critical thing for us to detect ahead of time and prevent. Right. And simulation is critical in order to do that. So once you've designed the system, you run this through the millions of miles of simulation. But then at the same time, you create some more intelligent-based pathological scenarios where you can still prove that in the worst-case scenario, my system would be safe.
Pathological scenarios. I like that
Yes.
phrase.
And the system has to survive that. That's
Right.
how we make sure that before every deployment, it goes through these kind of checks and rigorous checks.
Right.
But yeah, all the bells and whistles that ARM builds in and other things are very useful.
Excellent.
I think the
getting
other so the other factor. So we talk about sensors for radar, lidar. Yes, we need those, but I think we also need sensors on the equipment itself, because the equipment is going to change over time, right? So you drive 10,000 miles,
Yep.
maybe there's a little bit of wear and tear, and will your autonomous system still be able to react in the timely manner for emergency braking, or so those changes as the system gets deployed in the real world, you have to simulate those ahead of time as well to have confidence that this is going to even after deployment over a period of time, it's still safe. Because there's tiny changes in the physical world, everything adds up, right? So maybe there's a gears worn out a little bit, and some electrical signals maybe degraded a little bit. You add all of those things up, you could have a scenario that you don't want. So I think simulation allows you to expand the if you want to call it the design space, but also in the operating world, right? So you're changing the parameters to assess what the risk is. So I think that is going to play a key role to have confidence in the deployments as well. So.
Yeah, absolutely. I'm going to just pick up on that a little bit. So there is stuff you can do with hardware. We can age it to 10 years and see whether it's still reliable. So we do all of that. But on top of that, exactly what you mentioned, how do you sense the wear and tear, mechanical wear and tear,
Right.
within a moving vehicle or a robot that's embodying the physical AI system? I think that's crucial as a separate sensory input that goes into the algorithms that's running this, and it's a key part of what we built into our system as well.
Yeah.
I would just say one more thing is, I think this is a little bit how traditionally safety has been thought of, right? You design the hazard scenarios, you do analysis, but fundamentally, if you think about humans and how are we safe? What makes us safe?
Mm-hmm.
It's our actually ability to do reason
Mm-hmm.
and predict and simulate in our head scenarios. That is what makes it, we released the Alpha Mayo model, and we have right now one of the safest AI model for driving, and it's not driven by a lot of data, but it has the ability to reason, counterfactual reasoning to come up with what is the right outcome. So I think safety is required across the board.
Yeah.
Lots of models for physical AI are being trained by just imitation learning.
Yeah.
Nobody is doing an unsafe action during that imitation learning.
Yeah.
How does a model recognize that I'm in an out-of-distribution scenario? Yes, if I'm in an out-of-distribution scenario, that's where world models come in. You have to train it with a lot of different diversity of data so they can reason, they can do counterfactual simulation and thinking, and then come up with a solution, right? So it starts from data, what data you're using to train your model. Of course, you want to test your models in simulated world, create all kind of scenarios, which you've been not in long tail scenarios, hazardous scenarios, in simulation to test how your models are going to behave. But even then, that's not enough. You need to have the generative reasoning capability where it can simulate the different scenarios when it happens and make a decision. So I think, and this is all in complement to the basic stuff that we have learned in safety over hundreds of years, building automation, building machines, how to make sure that we can detect a fault, how can we make sure that the communication interfaces are safe. So, but in addition to all of the traditional things that we have learned, if we are moving to this physical AI, and we have to think about what does it mean from an intelligence layer?
Correct. I mean, again, it's just sorry, Frank, just to add one more point. I think the learning part that Amit just mentioned is just super critical. Again, it goes back to fixed function, limited task robots that we were used to a multi-function, multitask robots that we are actually, or autonomous driving cars, is what we are getting into, right? Because you can't predict every single scenario, so you will have to try and manage as much as possible in the simulation. Now, again, the key aspect from connecting this to safety again is, look, it's always going to be, the way we look at it is three-vector approach. One is you build enough, the hardware that actually runs the workload needs to be safe and needs to be built from as much safety concepts as possible. Then you also have to ensure that the software stack that sits on top of it also has the right hooks, basically, as what Prasun was saying, in order to exploit what's there in the hardware, right? So you sort of have a full stack solution that is safe and secure, in addition to being performant and all of that stuff. But the third vector is really the simulation environment that you can leverage on as much as possible before you deploy the model or deploy the workload in the real world scenario. So I think it's just all the three vectors absolutely have to play a super critical role in this whole thing.
Yeah,
Excellent.
I definitely want to echo that, because when we are entering from what we just talk about, right, a single task robot to a general purpose robot, that's when you need to think about the safety from a human level. Think about LLM, right? When LLM first is a chatbot, and currently you see like a robot doing a lot of very fancy dexterous tasks, but how harmful can it be, right? A better hardware and better control algorithm just don't hurt human. And then in LLM you enter into I would say the first generation of agentic, but that's mostly just orchestration. You already have the workflow. Just like in, for example, similar probably in self-driving car, you have all the rules as a baseline where you need to. Of course, I think Rivian, you have much more rules than we will see in our driver license handbook. But it's still you have a rule to follow. But no one give us, since we grew up, no one give us a rule of how Monica acts safely. What does it even mean, right?
Yeah.
And then now, in our environment, but then nowadays, right? Why we are so anthropic, right? Why are they so nervous about the new AI? Because it's totally agentic. It's making a very complicated, very long horizon risking now. But in robot, to be honest, we are not there yet, but we can definitely see it coming very soon. For example, when we are we work with restaurants, right? Yeah, now you are folding napkins for them, right? Very wholesome, right? But then you go into but your employee probably don't need to stay there just fold napkins all day. When I finish folding, there's some food. There's some food you can cut it. You can cut it off portion. Then you need to use a knife, right? Right, and you need to use a knife, and then you finish cutting. Then probably get some other, now you finish a sliver, let's get some carrot. So when you go get a carrot, please put that knife down before you go out. So when you have that long horizon, when you are entering into a more and more general intelligent robot, that's when you actually need to think about the intelligence and reasoning about that. That's a next, I would say, safety 2.0.
Bringing it back to Amit's point, why are we safe? And I agree, generalization, reasoning,
failure.
But also some of us aren't safe.
Yeah.
And so this is going to be an interesting journey.
So I would like to see how I believe there are a lot of things like that can be taught in simulation. So I would love to see how those rules are embedded in simulation or in the foundation model that we are building. That would be interesting.
It seems counterintuitive, but failure is important for learning safety, right? And the best way to fail is with reinforcement learning and simulation. Just fail as many times and learn what's bad.
Safest way to fail, for sure.
I think big thing is you can predict as a physical AI system, whether it's a robot or a car, you can predict what you're going to do, but the world around you is unpredictable.
Yeah.
And that's what this intelligent system, can it react in a low latency enough way to what's happening outside and safely? And that's where the efficiency of models and actually how low an energy with from a compute standpoint can that model deliver, that is crucial in all these mobile systems.
Right. Well, listen, we've got to wrap up here, and I warned you guys ahead of time. I wanted one prediction from each of you. This is a very fast-moving space, and I'm thinking by Cadence Live 2027, so a year from now, what will have changed in our world? What will we be able to do? Or what problem will be left undone because of its complexity? Let's just go down the line quickly if you have some thoughts on that.
Sure. So I think it's a hard question to predict. Hopefully I'll invest where I'm, what I'm going to say. But I do feel that in about a year, you'll start seeing what I like to call simulation-powered intelligence on the edge. Okay, so we talked about efficiency, and I do feel that simulation will get to a point where some decisions that are made by whatever device it is will be made on the edge. Okay, and that requires lots of changes, but I think we're moving there. I do believe that the engineering-grade simulation is going to get better, faster, so that it can be used not only for design, but for policy development, for validation, and eventually deployment on the edge. I think in a year, I expect to see some of that happen, and I think that will change lots of things for people in the simulation world. Okay. So.
Yeah, I think I believe like we're asking this question: is simulation useful? If you look at what's happening in LLM right now, all day long, they learn more is by simulation and RL. I think next year we will not be having this question. It's going to be very clear that reinforcement learning simulation, whether it's through word models, which is neural simulation, or it's through physics-based simulations, they are absolutely critical. The question is going to be, okay, what more can we do with this simulation?
Yeah.
Yeah, so 2027, besides AGI, right? Like what
Yeah, set that aside.
Yeah, set AGI aside. Yeah, I don't know whether it's like will be on 2027, but I do think that like if simulation is not just a tool for like companies like us, like developing a robot, like I'm hoping that in the future that it can be even on the marketplace, so that everyone, because our environment, like no matter how powerful the so-called general purpose robot is, the environment, the world is changing every day. Like I need to learn to use a new like espresso machine, right? When our company has one. So I think what if in the future, right, like when it's very easy for everyone to build a simulation of a new environment that they want like robot to interact with,
Right.
Is there a place I can upload it, and then our robot can chain on it before it's deployed, before it's shipped to the customer, or just like how you upgrade your FSD, right? Like the robot can just like upgrade itself over time. I think that's when we have a new ecosystem building and a new way to think about the human-robot interaction and evolving together. Hopefully that's 2027.
It will happen, Monica. It will happen. No, I think, again, let's talk about 2030 Cadence life first.
Oh, wow.
Right? I mean,
That's ambitious.
That's aggressive.
I know, because I'm just, talking to Mahesh. You're part of Cadence now, so things will happen. So, no, I think, we'll definitely have newer models next year, I'm pretty sure. The workloads, the world of workloads is just evolving so rapidly, so there's going to be a lot of new stuff that we will all consume and understand how to sort of build our systems for it. Now, again, we believe that it's a multifaceted sort of problem, and we're all, it's different ecosystems coming together, right? So we work with our silicon partners primarily to enable, the models of the compute elements and the SoCs and all of that stuff, like the digital twin of the SoCs and platforms. So we and the rest of the ecosystem will continue to work on that, and we'll probably have a lot more collaboration and a lot more work done in the next 365 days to go achieve that, maturity around that. And then, of course, there is, the whole physics engine side of the story that needs to come together, and that will have its own evolution, and that will have its own maturity in the next 1 year. But more importantly, the whole aspect of asset libraries, for robots and autonomous drive machines to basically sort of use the simulation environment in a much more confident way, you need to have a much more richer asset library of everything that the robots or the autonomous drive interacts with, right? So that's going to be it's going to see its own evolution. It's going to probably take a little bit more longer for the asset libraries to be more richer and richer. But then it's more about how all of these different layers interact and come together as well. So Again, that's why it's multifaceted. At the same time, it's like different ecosystems coming together, and I'm pretty sure every year we will make progress towards that. So by 2030, Cadence Live, it's going to be a beautiful world. So.
Yeah, I think the digital twin is super interesting to us because the more you can simulate, the more you can make things safer, and the efficiency of simulation. That's what I look towards within the next year.
Yeah.
If the efficiency of that simulation can increase, I can do billions of miles of simulation rather than millions.
Yeah.
And that just gives us a higher level of confidence on deploying any of these physical AI systems. So that's where I see the improvement with all the efforts that people are putting in.
Well, if any of those predictions come true, I hope you'll come back to tell us about them.
Yeah.
I want to thank you guys for coming this morning and participating in this.
Thank you.